Hi, this lesson is about computing the area between curves. So we're going to call our area A. So suppose area A is the region bounded by the curves y equals f of x, y equals g of x, and the vertical lines x equal to a and x equal to b, where f and g are continuous and f of x is greater than or equal to g of x for all values of x on an interval from a to b. When that's the case, you can compute the area with this integral. The area is the integral from a to b of f of x minus g of x dx. If you think back to the definition of the definite integral, which is the Riemann sum, the f of x minus g of x is what I would consider to be the height of a rectangle, and the dx is my width, or my delta x, which is the width of the rectangle. So that's why it's important to know which function, when you're dealing with more than one, which function has y values that are larger than the other so that you know how to subtract your two functions in order to compute the height. Your height should be always the larger y value minus the smaller y value. So here's an example below in orange. We want to find the area bounded by f of x equal to e to the x, g of x equal to x squared, x equal to 0, and x equal to 1. So x equal to 0 is the y-axis. X equal to 1 is here to the right. E to the x is larger than x squared between 0 and 1. So when x is 0, your e to the x is this point here, 0, 1. When x is 1, your point is 1e, and remember e is about 2.7, so it's a number close to 3, so that's that point in blue to the right. Then for y squared, when x is 0, you're at the origin, and when x is 1, you're at the point 1, 1. So throughout the area, and it's shaded in orange, the e to the x function is greater than the x squared function. And this little purple strip in the middle of this area is just a representation of what a rectangle would look like. And remember, when you're computing an integral, there's infinitely many of these rectangles whose areas are being added up all together. Again, going back to the Riemann sum. So if you look at that rectangle, the depth of that rectangle is with respect to x. That's a delta x. And what that's telling you is that your integral, your limits, and your functions should be in terms of x. So that's exactly what we set up here. We have the integral from 0 to 1. And again, these are the x values. X is 0 and x is 1 here at these right-handed points for e to the x and x squared. The height of this representative rectangle will be e to the x minus x squared dx, which is your differential. All right, so now we take the antiderivative. The antiderivative of e to the x is itself. The antiderivative of x squared is 1/3 x cubed. We have to evaluate that from 0 to 1 by the fundamental theorem of calculus. Remember, always plug in the upper limit first. So you plug in 1 first and then subtract when you plug in the lower limit. So when you do that computation, you get e minus 4/3 as your area, which is a positive number, which is what you expect because you can see that this area is above the x-axis. All right, so sometimes the boundaries of your area is not obvious, and therefore you won't know the limits of the integral. So when you do not know the boundaries or the limits, then you have to first determine where f of x and g of x intersect. And we do that by solving this equation. We set f of x equal to g of x and solve for the value or values of x. So my next example is exactly that situation. I have to find the area bounded by f of x equal to x squared and g of x equal to x plus 2. We're going to sketch both curves. All right, so first we find where they intersect. So as I just mentioned, set them equal to each other. I have x squared equal to x plus 2. That's a quadratic equation. We solve quadratic equations by putting them in standard form, meaning set it equal to 0. This one is factorable. You get x minus 2 and x plus 1. So we have two solutions, x equal to 2 and x equal to negative 1. Remember that those two solutions represent your points of intersection. So in order to graph this properly, you need to know what the corresponding y values are. Now you can plug it into either f of x or g of x, but when you do, you get that the y value is 4, and that's the point I plotted here. And when you plug in negative 1, the y value is 1, and that's the point that's here on the left side, negative 1, 1. Okay, so in terms of graphing the two equations, the parabola is in green below. That's x squared. Remember, x squared has a vertex at 0, 0. Always show the vertex of a parabola on the graph. And so that's the green curve, and the line g of x is the blue. And so you can just connect negative 1, 1 and 2, 4, and that gives you your line. So here again, clearly, when you're setting this up, you can see that the line, the y values of the line are greater than the y values of the parabola throughout that shaded area. And that orange strip is my representative rectangle. You can draw a representative rectangle anywhere in the space. It doesn't have to be in the middle, just somewhere in the space. But you have to be able to visualize that if you started from the left-hand endpoint all the way to the right-hand endpoint, in other words, from negative 1, 1 to 2, 4, you have to make sure that your function x plus 2 is greater than or equal to x squared all throughout that shaded area. And it is in this case. Okay, so here's my area then. I want to integrate from negative 1 to 2. And again, negative 1 to 2 come from the x coordinates that we computed when we solved here earlier. And then you take your line, x plus 2 minus your parabola. That gives you the height of the rectangle times the differential dx. Okay, these are this is again another very straightforward integral. Anti-parallel gives you 1/2 x squared. Antiderivative of 2 is 2x. Anti-power rule for x squared is minus 1/3 x cubed. When you plug in 2 and then subtract out the negative 1, you get an area of 9/2. Again, a positive number. That's expected because your area is above the x-axis. Okay, so let's do another example. This one is regarding two trig functions. So we want to find the area bounded by y equals cosine of theta, y equals sine of theta, theta equal to 0, and theta equal to pi over 2. And we're going to sketch the graphs and shade the represented area. Okay, so cosine of x is the blue curve. Cosine of 0 is 1. Cosine of pi over 2 is 0. So it curves downward from left to right. The sine function is the green. That's increasing from left to right. Sine of 0 is 0. Sine of pi over 2 is 1. So these two curves intersect at pi over 4. So you might remember that from trigonometry, that cosine and sine are equal at when the angle is 45 degrees, and 45 degrees is pi over 4. That's the midpoint between 0 and pi over 2. Okay, so now we have our two vertical lines. When theta is equal to 0, that's my y-axis, and theta equal to pi over 2, well, that's this dotted line all the way to the right. So when I look at the area that's bounded by all four of these, well, I have two parts, and they're shaded in purple. So I have a part here on the left. That's my first area, and then I have another part here on the right. So you don't include this one here unless I said for y equal to 0, because then that would mean that I would be using this axis that I'm calling theta. So we don't include this part that I put a little question mark on. All right, so that means I have to set up two separate integrals, because on the left side of this area, my blue curve, or my cosine, is greater than my sine function. And on the right side of this area, sine is greater than cosine. So I'm going to have to compute the height in two different ways. In other words, the order of how you subtract your functions is different. My integral is set up is right here. My first integral for the area shaded on the left is the integral from 0 to pi over 4 of cosine of theta minus sine of theta, d theta. Then the area on the right is the integral from pi over 4 to pi over 2 of sine of theta minus cosine of theta, d theta. We add these two integrals together because we want to know the total area. So we have to take the area computed with the first integral plus the area computed by the second integral to get the total area. All right, so in line 2, you're taking the antiderivative. The antiderivative of cosine is sine. The antiderivative of minus sine is positive cosine, and we evaluate that from 0 to pi over 4. So move on to the second integral. The antiderivative of sine is negative cosine. Remember, because the derivative of cosine is negative sine, if I need for this to be positive, going back and forth, you have to put a negative in front of cosine. And the antiderivative of negative cosine is negative sine. So be really careful with your positives and negatives when you're dealing with sine and cosine with integration and a derivation. So the second integral has to get evaluated from pi over 4 to pi over 2. So in this third line, we're using the fundamental theorem of calculus, part 2, where you plug in your upper limit minus your lower limit. But we have to do that twice. So that's the work that you see on this line. Here we're evaluating these values. You shouldn't need a calculator for these. These are angle values that you should know the trig value of pi over 4, 0, and pi over 2. So the sine of pi over 4 is root 2 over 2. The cosine of pi over 4 is root 2 over 2. The sine of 0 is 0. The cosine of 0 is 1. Cosine of pi over 2 is 0. Sine of pi over 2 is 1. Then we're back to cosine of pi over 4 is root 2 over 2, and sine of pi over 4 is root 2 over 2. All right, so all of these root 2 over 2s, there's 4 of them. So that gives me 4 root 2 over 2. And then my two constants here, negative 1 minus 1 gives me minus 2. 4 root 2 over 2 simplifies to 2 root 2 minus 2. Again, that's a positive number, which is expected. So let's move on. All right, so here's another one where we have to compute how the region is bounded. And this time I've given you two parabolas. So we want to find the area of the region enclosed by y equals x squared and y equals 2x minus x squared. Sketch the graphs and shade the appropriate region. So as I mentioned before, we want to set them equal to each other and solve the equation. So this is also a quadratic equation. So we're going to subtract x squared from the right side to the left side, then factor, which is what you see on the third line. So factor out 2x. It's got a common factor of 2x, and you're left with two solutions right here, 0 and 1. And as I mentioned before, you need to know what the points are. So you plug in 0 and 1 into any one of the two equations, and you get points of intersection of 0, 0, 1, 1. So when we graph this, you're going to want to pay attention to the types of graphs that these are. Since they're both quadratic equations, you should figure out what the vertex is of, or the vertices are for each of them. So for x squared, the vertex is 0, 0. So we've graphed that one just a few minutes ago. And for 2x minus x squared, well, I did it here on the side in green. I used the derivative to do that. Remember, when the derivative is equal to 0, for a quadratic equation, you are that value of x will give you the x coordinate of the vertex, because that will be either the highest or the lowest point on the graph. This parabola is facing downward. It's an upside down parabola because the leading coefficient is negative. So I expect my vertex to be a maximum point. So when you solve this, you get x is equal to 1, and when you plug in y is also 1. So interestingly is that the vertex for the first parabola, 0, 0, is a point of intersection, and it's also a point of intersection for the second parabola. That's just a coincidence. It's not always going to work out like that. So here are the two graphs. I have x squared in the lighter blue below. My 2 points of intersection are plotted here in a darker blue. The other parabola, 2x minus x squared, that's in the green. And remember, that will be a downward facing parabola. So if you were to extend these out, my x squared would go like this, and my 2x minus x squared would go like this normally, right? But we're only interested in the part that's bounded. So that's that part in the middle that kind of looks like, I guess, like a boat or a canoe or surfboard or something like that. All right, so now we're ready to compute the area. So my area is the integral from 0 to 1. Remember, 0 and 1 were the values we found right here, the points of intersection, of the parabola 2x minus x squared minus x squared. Again, if you look at the representative rectangle that I drew here on the left in orange, the height is the larger values of the parabola, the y values, which are 2x minus x squared, minus the smaller values, which are x squared. So from this line to the next, you do a little bit of algebra, combine like terms, and once you do that, you're ready to integrate. Sorry, went down too far. All right, so now we take the antiderivative of 2x, that's x squared. We take the antiderivative of 2x squared, that's 2/3 x cubed. We evaluate this antiderivative at the limits, and so you get 1 minus 2/3, which has a value of 1/3. All right, so here's another one with two parabolas, but these are a little unique. We're going to be able to do this in a slightly different way. So we want to find the area bounded by f of x equal to x squared minus 6 and g of x equal to 12 minus x squared. Sketch the curve and shade the represented area. So just like the previous example, set the two equations equal to each other and solve for x. So when I do that, I actually chose not to do this by factoring. This one works out well for the square root method. So I added x squared over to the left side, and I added 6 over to the right side. So you get 2x squared equals 18. Divide by 2, you get x squared equals 9. Take the square root of both sides, you get x is plus or minus 3. Okay, so now you plug in to either one of the two equations. When x is 3, y is 3. When x is negative 3, y is also 3. So my points of intersection are negative 3, 3, and 3, 3. Okay, but because they're both parabolas, just like I mentioned before, you're going to want to know what the vertex is for each one. So if you remember anything about shifting, x squared minus 6, that's just a shift of x squared 6 units down. So the vertex is 0, negative 6. And in this case, 12 minus x squared, that's a reflection of x squared across the x-axis and a vertical shift 12 units up. So your vertex is 0, 12. All right, so you want to make sure that you plot your vertex for each of the parabolas as well as your points of intersection. So my points of intersection are here in purple. I have negative 3, 3 and 3, 3 on the right. My blue parabola is x squared minus 6. So you can see the vertex here below, 0, negative 6. And the green parabola is 12 minus x squared, and here is its vertex, 0, 12. So the area bounded by these two parabolas looks kind of like a football. It's all this space that I shaded in purple. And I drew one representative rectangle to show you that you compute the height within that space by subtracting 12 minus x squared minus the blue parabola x squared minus 6. Okay, so that's the area, the integral that I set up here. I want to compute the area from negative 3 to 3 of 12 minus x squared minus x squared minus 6. So be careful here because that minus belongs to the whole thing, so you have to distribute it. All right, so when I do the algebra for that integrand, there's some like terms. So you end up with this integral, the integral from negative 3 to 3 of 18 minus 2x squared. Okay, but these curves, the two parabolas, are unique in that they are both even functions. In other words, they are symmetrical on the left side and the right side of the y-axis. So you can compute the area by using this integral, or you can use the one below, which goes from 0 to 3, and then you are doubling that result. So from 0 to 3, we'll just compute the right side of the picture of the shaded area. But when you double it, you will get the area on the left side. So either integral works, but the second one, the one that I'm multiplying by 2, is easier to compute because of the lower limit of 0. So I'm going to do it with the with this integral here. So when I take the antiderivative, I get 2 times 18x minus 2/3 x cubed. When you plug in your limits, you get 2 times 18 times 3 minus 2/3 3 to the third power. When you plug in 0, both terms are 0. And then when you do the computation, you get 2 times 54 minus 18, which is 2 times 36. So you get an area of 72. Okay, so here's another. We want to find the area enclosed by y equal to the square root of x, y equal to 1/2 x, and x equal to 9. We're going to sketch the graphs and shade the enclosed area. So just like previous examples, I want to know where the square root of x and 1/2 x intersect. So because I have a radical, I square both sides to give me the next line, x equals 1/4 x squared. So that tells me I have a quadratic equation, so I set it equal to 0. So that's the third line here. Then you can factor out an x. That leaves us with x times 1/4 x minus 1. Set each factor equal to 0, and you get that x is equal to 0 and x is equal to 4. So just as in the previous examples, you're going to want to know what the corresponding y values are. So you plug them in to either one of the two equations, and you get points of intersection of 0, 0, and 4, 2. So, 0, 0 is here on the graph. That's your origin. And 4, 2 is here on the graph. That's the other point of intersection. So points of intersection are in this purpley pink color. All right, but I have this line x equal to 9 that I need to be concerned about, and that's the line here. That's a vertical line. So you're going to want to know where x equal to, what relationship x equal to 9 has with the two previous curves. So that's the work that you see here. When x is equal to 9, y is equal to the square root of 9. So this is the square root function, which has a value of 3. So 9, 3 is here, 9, 3. So my square root function is the curve in blue. Then you do the same thing with the linear function 1/2 x. When x is 9, y is 9/2, which is 4.5. So that's the point right here in green. So this is 9, 4.5. And so you connect the 2 points of intersection in this pink purple color to the one in green, which is 9, 4.5. And there's the line y equals 1/2 x. So when I look at this, I again have a situation where I have an area to compute that I have to split up my integrals in two different parts. One from 0 to 4 and the other one from 4 to 9. Okay, so I have the integral from 0 to 4 of the square root of x minus 1/2 x. So square root of x is the blue curve and 1/2 x is the green. Plus the integral from 4 to 9, and this time the line is greater than the radical. So I have 1/2 x minus square root of x. Then we have to take the antiderivative. And we add the two integrals because we want the total area. So for the first antiderivative, x square root of x is x to the 1/2. Do anti-power rule. So we get 2/3 x to the 3/2. Anti-power rule again on 1/2 x gives you minus 1/4 x squared. Evaluate that from 0 to 4. Take the antiderivative of the second integral. That's 1/4 x squared minus 2/3 x to the 3/2. And that one has to get evaluated from 4 to 9. So in the next line, we are inputting my upper and lower limits. So we get 2/3 square root of 4 to the 3rd power. Remember, when you have an exponential expression, that can get rewritten as a radical. This is the same as the square root of x to the 3rd, and that's exactly what I'm doing on this third line. So I have 2/3 square root of 4 to the 3rd power minus 1/4 4 to the 2nd. When you plug in 0 to those two terms, the whole thing is just 0, so I only wrote 0 once. Then we plug in our upper limit here for the second integral. So I have 1/4 9 squared minus 2/3 square root of 9 to the 3rd power, and then substitute in the lower limit. And when you do that, you have to subtract. So both terms change signs. So this one becomes a minus and this one becomes a plus. So it's minus 1/4 4 squared plus 2/3 square root of 4 to the 3rd power. So the rest of this is just some arithmetic. Be careful with your fractions. You eventually get to a point where you need a common denominator, which is 12. And when you compute that, you get that your area is 59/12. Okay, so now we're going to look at this from a different perspective. This will be considered horizontal elements. So you can find the area of a curve when you express your equations as functions of y instead of functions of x. And so suppose I have x equal to f of y and x equal to g of y, and we have two horizontal lines, y equal to c and y equal to d, where f of x and g of x are continuous, and f of y is greater than or equal to g of y for all values of y on this interval from c to d. Okay, so we're kind of looking at this opposite of what we were doing with the previous examples. We're looking at this in terms of horizontal elements. So in other words, your rectangles, your representative rectangles will not be vertical. They will be going from left to right. And so when you're determining the order of how to subtract, right, this will now be considered the length. I won't call it height because they're going to be horizontally oriented. This will be the length of the rectangle, and this one here will be your width of the rectangle. So when you're trying to figure out the order of how to subtract, f of y should be further to the right than g of y. That means f of y would have greater values than g of y. Okay, so that's just repeating what I just said. So we want to find the area bounded by y equal to the square root of x equal to 9, and y equal to 1. Okay, so I'm going to do this with horizontal elements. This one could have easily been done with vertical elements as well. Sometimes vertical and horizontal make no difference in terms of complexity, but in some cases it does make a difference. So it's good to know two different ways to compute these. So here's my graph. So my square root function is a curve. It's this bluish color. So I only need to compute it where x is 9 and where y is 1. So when y is 1, x is 1. So that's this point right here. And when x is 9, my y is 3. So that's this point right here. So we just need to connect those two. So and here's the line y equal to 1, which is part of the boundaries, as well as the line x equal to 9, which is part of the boundaries. Okay, so if I draw a representative rectangle, I drew it here in orange, the height of this rectangle would be determined by the length of, from here to here, these are 9 units. And from here to here, well, that's the value of your function. Okay, but if I'm going to do this in terms of y, notice that the depth of this is with respect to the y-axis, not the x-axis. That means I'm going to have to restate y equal to square root of x in terms of x as a function of y. So when I do that, you square both sides and you get that x is equal to y squared. So my length of my rectangle is going to be 9 minus y squared. So it's the 9 units that I pointed out here minus the y squared units, that's this smaller piece right here, will leave me with the length of that orange rectangle that I drew below. All right, so that's my length. And then my differential is dy. And since I'm integrating with respect to y, my limits should also be y values. So my y value goes from 1 to 3. So I go from 1 to 3, 9 minus y squared dy. Okay, so take the antiderivative. You get 9y minus 1/3 y cubed from 1 to 3. Plug in your upper limit and then plug in your lower limit and subtract. And when you compute the result, you get that your answer is 9 1/3 or 28 over 3. Okay, so here's another. We find the area bounded by x equal to y squared minus 2, x equal to e to the y equal to -1, and y equal to 1. All right, so these this example should be obviously done in terms of horizontal elements. Both of my functions are expressed in terms of y, so that's always a good indication that that's the right way to go. My boundaries are also specified in terms of y, so those are 2 horizontal lines. So first let's sketch the graph. So my 2 horizontal lines are here in this dark pink color, y equal to -1 and y equal to 1. Okay, e to the y, x equal to e to the y. Remember, if I have x equal to e to the y, if I took the natural log of both sides, you would get ln of x equal to y. So x equal to e to the y is actually your ln of x function, which is this curve here in blue. Remember, it goes through the point 0, 1. Its domain is all positive real numbers. The closer you get to 0, it goes to -infinity. So that's your curve for x equal to e to the y. And this other curve, x equal to y squared minus 2, well, that's a parabola. It's a sideways facing parabola. It doesn't have a y term, so it's just a shift to the left. So I have a vertex here at -2, 0. Okay, and then it's facing to the right. Okay, so the area that you shade is the area here in purple that's bounded by all 4 curves. So when I look at this in terms of horizontal elements, I drew my representative rectangle in orange. The depth of that rectangle is definitely with respect to y, so it's got a delta y associated with it. So when I compute my area, I have the integral from -1 to 1. And then I want to subtract the function that's further to the right minus the one that's further to the left. So I have e to the y minus y squared minus 2. In this line, I just distributed the negative. Then I took the antiderivative. The antiderivative of e to the y is itself, e to the y. Antiderivative of y squared is 1/3 y cubed. Antiderivative of 2 is 2y. Plug in your upper limit and then subtract out your lower limit. So make sure you distribute that negative. And you end up with this result here, e minus 1 over e plus 10/3. Okay, so here's another example. We want to find the area enclosed by y equal to x minus 1 and y squared equal to 2x plus 6. Sketch the graphs and shade the represented area. All right, so this time it might not be quite as obvious. Is this going to be horizontal or vertical elements? Notice that this one is a typical line, y equals x minus 1, but this one's unusual, right? This would not be a function. So we really need to see what this looks like before we determine how we want to compute the area. So the process is the same. We want to set them equal to each other, but I can't set them equal to each other in their current state because one is y equals and the second curve is y squared. But if I square the first one, which is what I did here, then you're really setting y squared equal to y squared. So I have 2x plus 6 equals x minus 1 squared. All right, so I'm going to expand the right side, which is what you get on line 2, and then you can see that you have a quadratic equation. I'm going to set it equal to 0 by subtracting 2x and subtracting 6 over to the right. So I get x squared minus 4x minus 5. That's factorable. So I get 5 and negative 1 as my points of intersection. And just as I mentioned previously, you want to plug in to your equation. The first one is the easiest one to work with. So when x is 5, y is 4. When x is negative 1, y is negative 2. So I have 2 points of intersection, 5, 4, and negative 1, negative 2. So those are the 2 points that you see here on the graph in like this purpley pink color. All right. So it's easy enough to graph a line. So if you have 2 points, just connect the 2 points here for y equals x minus 1, and that gives me the line in blue. Okay, but we need to graph this y squared equals 2x plus 6. All right, so if I were to solve this for x, you would get x equals 1/2 y squared minus 3. This again represents a sideways parabola with a vertex at 0, negative 3. So that's the point here. So it's facing to the right. It goes through the 2 points of intersection, the 2 purpley pink points. Make sure you show the vertex on there. So that's the green point all the way to the left. So the area that's bounded by this is this piece here, shaded in, again, this pinkish kind of color. And so now we have to figure out, do I want to integrate this with respect to x or with respect to y? All right, so if I were to integrate this with respect to x, it would create more trouble for me than with respect to y. So let me show you quickly why that's the case. All right, so this is sort of what this graph looks like. Now, this one doesn't look quite right. So I'm trying to reproduce what I did above. Okay, if I were to create vertical elements for this, in this, if I were to draw a rectangle in this space right here, the area or the length of this rectangle would be determined solely by the sideways facing parabola, because my height would be determined by the values of the y values on that parabola. But once I transition past this point of intersection right here, the height would be determined by the parabola minus the line. So with vertical elements, I would need 2 integrals. But with horizontal elements, that's not the case. So look at this height that I've indicated here in this orange bar right there. If I were to look at that orange bar from the bottom point, -1, -2, all the way through to 5, 4, my line, my blue line, is always greater than my green parabola. So 1 integral is sufficient. So you really need to look at the picture and have an accurate graph when you're determining what your strategy is. All right, so if I'm doing this with horizontal elements, that means I need to do a little bit of work because everything should be expressed in terms of y. So the work is here. That's what I showed you I want to express both as a function of y, and my limit should be in terms of y. So remember, my y value here is -2, and my y value here is 4. So my limits go from -2 to 4, and then I have my line, which is x plus 1, minus my parabola, which is minus 1/2 y squared minus 3. All right, so I distributed the negative on this line, and on this line I combined my constants. So now I'm ready to take the antiderivative. So the antiderivative is here. I have a is equal to -1/6 y cubed plus 1/2 y squared plus 4y, evaluated from -2 to 4. Plug in 4, and then plug in -2. Make sure you subtract and then distribute that negative across. And when you do the computation, you get an area of 18. Okay, so you're ready to try the homework for this section. Good luck.